Hey guys, welcome to this walkthrough of the Capstone project. Thank you for watching this video, and I'm sure that it's going to be very helpful. So, okay, let's start. So, what is this project about? Well, the name of the project tells a lot about it. It is related to using blockchain to real estate. So, what we're going to do is that we're going to create mint property titles, and we're going to list these properties on a platform for selling these titles, these tokens, these ERC-721 tokens. So yeah, it is basically that is how it is our work, like a little introduction on how you could sell properties using blockchain, and well, all of the benefits that come with that. So first, I want to introduce you to OpenSea. OpenSea is a decentralized marketplace used for selling crypto assets, such as CryptoKitties and other digital assets. So you can post their tokens, ERC-721 tokens, and sell them. So in this case, what we're going to do is we're going to create our tokens representing our properties, let's say your house, your apartment, and putting them on this marketplace and being able to sell them for Ether. So yeah, it is really interesting. And yeah, basically what we're doing here is we post, and people can just go into the website and buy them if they have the money, or even they can offer, it can function in an auction kind of way, so people can offer and you can have many offers. So yeah, it's basically it. So I'm going to show you the final, let's say, a product with OpenSea. So what we're going to see is this one. So this is the marketplace that you should create, obviously with another name. But it's basically it. So in here, you see that I created 5 properties. In this project, you have to create 5 properties. And if you see here, well, you can filter them by categories, search for them. And this is your marketplace there in OpenSea. So it's really, really cool. If we want to see a property, we just click on it, and it displays there the property. And well, as you can see, you can buy it. You can set a description, a photo. And here you see the activity. So in this case, what we're going to do is to create the token. So if you see here, I created it. Here I started the sale and I sold it. That is what we have to do in this project. So what we're going to do is to create the token, put it for sale, and sell it with another address that we own. Okay. So yeah, it's basically it. As you can see, you can do this right now. You can put anything on sale. Well, this is the Rinky, but it applies. It could also apply to the real net, to the main net in Ethereum. So it's really, really cool. So let's go to the next thing, Socrates. Okay, Socrates is really, really interesting. It is a succinct zero-knowledge proof, and it gives us 2 things. One, it gives us security. It also is used for enhancing privacy and scalability in the blockchain. So basically, what we want to do with Socrates is that we want to use it to prove that we own a property without revealing, let's say, any information related to a property or any private documents that, let's say, entitle us to a property. So that is Socrates. Socrates is you prove that you know something without revealing what you know. So that is why it's called zero knowledge proof. So it is basically how it works is that you create a file where you compute something, and you know what is the right input, so that the computation is successful. And well, if the computation is successful, that proves that you know what needs to be input into that function to make it work. Okay. So yeah, it is basically that. So I'm going to give you a little example. I'm going to introduce Socrates. Sorry. Socrates zk-SNARKs. Socrates zn. Okay, so let's start in here with Socrates. 1 second. It seems that I'm having a problem to find the link. 1 second. Socrates. Okay, here. So okay, I recommend that you get into this website of Socrates and try to explore it. I recommend the tutorials. So try to check out the getting started tutorial, and also the tutorial for proof of image. So what we want? Let's see a little bit of this tutorial. So in this tutorial, we're proving the knowledge of a hash preimage. What is a preimage? It's very easy. Is anything that you pass to a hash function and that you want to hash. So let's say a document, or I don't know, a string, a sentence, anything that you want to hash is what is named a preimage. So what we want to prove here is that we know the preimage of a hash, what we input, like what was created to a hash, like let's say the preimage of the hash, what we inputted to a hashing function and resulted into a hash without revealing what is the preimage. So that is why it is awesome and also protects our privacy. We are not showing the preimage. We are to prove that we actually know the preimage that produces the hash, and that is basically it. So you can do the same with a password. Let's say you can create a system where a special password, and you can prove that you know the password without revealing the password. So that is actually what we want to do in this project. We're going to we know a password to a property, and we want to prove that we know that password that belongs to a property, basically. I'm going to include these links on the description of the video, so don't worry. So yeah, basically what we need to do is to follow the instructions in here. So yeah, you need to install Docker first, run Socrates. Here is the path to the folder of your project, so the one that you downloaded, and the path that in your finder of the project that you just downloaded. And here, well, you run it, and yeah, that is basically it. You run the Docker, and it runs the software, and what it does is that well, let's continue. So you have to continue with doing the thing. So what you need, let's continue to see what you need to do. So yeah, it's a 5-step process. First, you need to create a program and compile it. Next is the trusted setup. Then you compute the witness. Then you generate the proof. That the proof is what proves that you know the thing that you want to prove. And yeah, next you export the verifier. That is the document, the contract that you use that you can use to verify that you have a correct proof, a valid proof. So let's see it. So in here, what we're going to do is that we need to, well, in this case, in our project, we have one file that is called, let me see here what it is, Socrates. Okay, it's a square.code. So here is what we're going to create that mysterious computation. That is, no one is going to know what is this computation about, just us, that we want to prove something. And yeah, we're just going to compile, well, fill this file with the variables. So you actually just need to use this one. And in this case, what we want to do here is that the special computation is that we know a number and it's square. So it's basically it. So let's say that is the password that we know and we don't want to reveal, and that we prove it right here. That is that we know that to prove that we own that property, let's say the special password is a number and it's square. Obviously, this is just a simplification for this project, but you can do many kinds of things. So let's say you can use a special document that is emitted when you own a property. So what you pass is the document, and it creates a preimage and creates a hash. Sorry, the document is the preimage and creates a hash, and you prove that you know the preimage to that hash with proofs that you own the property, or that it can be also done with a password that just the owner of the property knows. But in this case, we're just going to simplify it and say that the special password that just the owner of the property knows is a number and it's square. So yeah, we use the square.code. Well, in here we compile it. We generate the trust setup. That we compute the witness. That here what we do basically is that we pass the input to our square.code file, and we do a computation, and it does the computation to prove that it does the computation with the inputs that we give it. So the inputs here would be the number and the square. And with that, we generate the proof, obviously, if the previous step we passed the correct input to our function. And this proof is what we are going to use to prove that the computation that we did was correct and that we actually know that password that only the owner of the property knows. And then what we do is to create the verifier smart contract. That basically what this contract does is that we pass it the proof to the contract, and the contract tells us if the proof is valid or not. So that way we can upload a smart contract to Ethereum, and it is used so that people using the system can verify if the proof that we used is correct or not, and the system also can use that if the proof was correct or not, and to prove that if the property actually belongs to that person or not. So these are just the results of running everything. So actually this is just a result of compiling, and this is the input that you're going to get, the output after running each of the steps, basically. So I also wanted to share with you some cool links. I'm going to include it in the description, and these are links to knowing a little bit more about Socrates, and you can also understand better what Socrates is about and its special properties. So it's really cool, please watch them. So let's, okay, the project steps. So the first thing is obviously clone the project, explore the code base. So let's explore a little bit the code base. So this is the project. We're going to work in this folder and in this folder. In here we have the square code, so we need to edit this code, and you just have to fill the names of the properties here, basically, and there is nothing else that you need to do. Optionally, you can do something more complex, like proving the knowledge of a preimage, but in here it is good enough to prove that you know a number and its square. Okay. As a tip, I suggest that you try to, when you do that, try to look at the getting started document link, please, in here. Now let's just follow the steps in here. So the first thing is fill out the ERC mintable document, contract, sorry. So basically there, what you are going to is to fill different to-dos. Just follow the to-dos. You're going to find it useful to look at OpenZeppelin. So please look at the OpenZeppelin, because you can do one of two things. One, use some of the files from OpenZeppelin, or use them directly in there, because as I'm going to show you in here, we're going to need to fill out, let's say, the ownable, the pausable contract. So basically, what you can do is you can go to OpenZeppelin and also import, use these contracts that are available in OpenZeppelin, and make sure that they comply with the tools, basically. So yeah, after you do that and complete everything here, I don't think that there is anything weird. Just complete the tools. What you need to do is to test it, okay? Test it. So where you need to test this final contract that you create, okay? This one. So please don't for that test file, you need to test this thing, and please don't test another thing, because that is a common error that students test another file. No, test this one, okay? So that is really important. Test this final contract, and well, obviously not necessarily just this contract, but this file, the contracts in this file, okay? Because sometimes people are doing that, they're testing other files, because we're going to inherit some of the functions from these contracts in another file, so that is not correct. Please test this file in tests ERC 721 Intel. So let's look at that file. Sorry, tests. So we implement the test for that file in here. And basically what you need to do is just do these tests. If you want to do more tests, that is okay. But at least you need to complete all of these tests, okay? So yeah, that is basically it. Look down here, it says ERC 721 mintable complete. That is actually referring to the last contract that I talked about. So when they talk about that, they're actually referring to this one, okay? So they're actually referring to that we import in there is actually this one, okay? The custom ERC token. That is, nothing else. So yeah, just I'm going to mention this again because this error is frequent. So it is important to have that clear. Sorry. So in here, when we import this contract, we're actually well, because we don't have a name defined yet, but basically this contract is referring to a contract in this file, and is referring to the last contract in here that inherits from all the previous contracts that are above. So this is actually referring to this one. Custom ERC token is actually the one which we should import in here. Or if you want to actually use this name, there is no problem, but copy this name and use it to name the contract in here. Basically, that is it. So let's continue. Now you implement Zokrates, so you install Docker, you complete the square code that I already mentioned. So in here, and sorry, in here, you complete this one. As I said, it is acceptable just to follow this computation that is just proving that a number, that a square, that a number, let's say that E is that A, sorry, that B is the square of A. So it's basically that's the computation that we want to prove. So A squared equals B. Practically, that is all that we want to prove, and that is valid. So you can just fill the name of the variables there. But if you want to do something more complex, to make an even more impressive project, you can do it. Like to prove a preimage of a hash, or a special way to prove a more complex password. So try to explore that if you want to do an even better project in this application with Zokrates. So you compile the program, compute the theme, and well, basically you just need to follow the steps in here in Zokrates. You follow those steps, and you'll be awesome. And here where they say well, export the verifier.sol. So as you see in here, Zokrates is going to output a file that is called verifier.sol that has the verifier contract. In here, in this project, we name it a square verifier because we're verifying the square. So you need to make sure, well, when we say verifier, we actually are referring to a square verifier. It's the same thing. So I'm going to say it once again. Verifier.sol is actually referring to a square verifier. So the same thing. So let's see in here. Sorry. Okay. Let's go to the tests. So you actually need to include that verifier in here, in contracts. So add the verifier code in here that you produced in here, in this step. You need to add it in here. And as you can see, this one. In this one, what you just you need to this test square verifier is actually the test for this, as I said. So you can do you can just change the name if you want, or use the original name that is verifier. There is no problem. And you basically need two tests. One, with the proof that you created in this step. You need to prove in here that the proof is correct by calling the special function in the verifier contract that proves it, and also prove an incorrect proof. Okay, so you create a fake proof and pass it, and make sure that the verifier contract returns an incorrect proof. After that, we need to do an integration between the ERC27 and the zk-SNARKs. So it is basically that we're going to create a new contract that uses, first of all, the verifier.sol that we created in Zokrates, and we're going to let's say put it all to also combine it with the final contract from here. That would be this one, the custom ERC token. Okay, so what we're going to do next is combine the verifier contract and this one, so that I'm going to show you later why, but that is basically what we're going to do. So let's see that file. So we're going to do that in this other file that is called Salt Square Verifier. Okay, so yeah, I said we're going to combine it. No, we're actually not going to combine it, but we're going to use them both. So that is a clarification that I want to do. We're not going to combine the both contracts, but they're going to work together. So they're going to work together for the system. Okay. So basically, what we need to do is to in here, like we did in the flight surety project, we just need to import the verifier and pass it to the custom ERC a contract. So it's basically what we need to do is that from the custom ERC contract, we're going to call from it the verifier function, the verifying function from the verifier contract, and we're going to deploy both of those contracts. So just follow the instructions here. Basically, you need to, as I said, import the contract from this one and inherit from it. And basically, what we are going to do in this other function is that before we are able to mint a new token, our contract, this contract, is going to call the verifier contract to verify that the proof that was passed in the mint function was correct. And if it is correct, then it proves that we own the property, and therefore the property can be minted. It's basically that. I just want to make something clear, and is that each solution, you need to make sure that each solution needs to be unique. So for that, you're going to use the mapping, and well, to make sure that is unique, I suggest that you use a hash of the solution. So you create a hash of the solution, and that way you can make sure that there's just one hash for that solution. Well, after that, you need to deploy the contracts, okay? Both contracts to Rinkify, and mint 10 tokens, okay? After that, you need to generate the OpenSea marketplace. I'm going to share one special link that shows how in the description of this video. And then what we need to do is to list 5 tokens in the marketplace and then purchase those 5 tokens. So if you want to how do you verify that you listed 5 and you purchased 5? So first of all, when you created your store like this one, you need to see 5. And to make sure that the purchase was actually done, you need to make sure that you have the sold event. Okay, guys, so that is basically it. Thank you so much for seeing this walkthrough of the Capstone, and I wish you the best. Thank you. Please, if you have any questions, please post them in the comments in this video. Also, one last thing is that, first of all, try to, if you have any questions, also try to look at the knowledge page. Here we have added some frequent questions, and also if you have a new one, please add it. And also there is a FAQ, frequent asked questions for this project. I'm going to also add the link. Okay, guys, bye, thanks.